Swayam Prabha. Digital India. Educated India.
Welcome back. Now we are going to start the mathematical part thereof. So before I start the mathematical part, I am going to tell you what are the various types of mathematical thinking you need to be able to succeed in data science. First is, I want to realize that everything we do computationally is couched in a finite dimensional computational domain. A problem may have infinite structure, but computationally I can do only finite things. So, ultimate aim in data science is to be able to compute and do things. So, the finite dimensional computational problem is what we have to solve. So, what are the appropriate mathematical tools that are needed to be able to perform all the tasks? First is the notion of finite dimensional vector space, then properties and classifications and of various matrices, then tools from multivariate calculus, tools from optimization theory. There is also a tool from probability theory and statistics. I am not planning to cover the probability theory in here. I am sure you all must have had a course in probability theory, but some of the important statistical concepts we will introduce later. So now I am going to start with the mathematical foundations of finite dimensional vector space. Capital R represents the set of all real numbers. A real number is also called a real scalar. The sets capital C is called the set of all complex numbers, is also called set of complex scalars. Rn, r to the power n, simply called Rn, the set of all real vectors of size n. Cn, set of all complex vectors of size n. If I say x belongs to Rn, so this is a symbol that tells you belongs to, I am sure you are all familiar with. X belongs to Rn implies x is a real vector with n components, x1, x2, xn. Each of the component xi's are real numbers. 0 is a real vector. The context will tell you the size of this vector. So when I am working in Rn, 0 represents a real vector of size n, all of whose elements are 0, 0, 0, 0. If you consider a real line, the origin is 0. If you consider a two-dimensional space, origin is 0, 0. If you consider a three-dimensional space, the origin is 0, 0, 0. So origin is a vector whose components are 0, and origin is a part of Rn for every n. This vector, all of whose elements are 0, is called a null vector. So what is an example of a 3 vector? A vector of size 3 in R3, 3.2, 1.5, 9.9. I know you know those things, but I want to be able to make sure that I cover all the basic things. Let the Cn be the set of all complex numbers. X belongs to Cn implies x is equal to x1 plus iy1, x2 plus iy2, xi plus iyI. Well, I want you to understand, I am using I here as a complex number. Sometimes I use I as an integer subscript as well. If the occasion needs, you can change the complex number I to j. You simply need to define, you want to have a name. Xi, yi are real, I is square root of -1. So what is a typical example of a three-dimensional complex vector? 1 plus I, 1 minus I, 1 minus 2I. That's a three-dimensional complex vector. We will largely deal with real space, real vectors, but for example, in quantum mechanics, complex numbers arise very naturally. So many of the problems in quantum mechanics can be formulated as a problem in complex vector space. So data science involves problems in quantum mechanics as well. So depending on your needs, I can work in the n-dimensional real vector space or n-dimensional complex vector space. I use the word vector space without defining what it is. I simply define the notion of a vector, real and complex. Now I'm going to talk about operations on vectors, which I'm sure you all know. We are using symbolisms. So x, y, z belong to Rn means what? X, y, z are three real vectors of size n. A, B, C belongs to, it should be R, that should be R, not Rn, sorry, real numbers. So x has x1 to xn, y has y1 to yn, z has z1 to zn. Transpose of a vector. So I wrote the x, y, z are all columns. So I wrote it as a transpose, and transpose operation is given as T. So column is a transpose of a row. I can define operations on vectors, addition, subtraction. So x plus y refers to component-wise vector addition, component-wise subtraction. If I multiply a vector by a constant a times x, you multiply every element of the vector by a constant. That's called scalar multiplication of a vector. Then there's an operation called SAXP, scalar times a vector plus a vector. I have two vectors x and y. I multiply x by a, and then to this product I add x. So zi is equal to a times xi plus yi. So scalar times a vector plus a vector. So these are the basic fundamental operations on vectors. So we saw the space of real vectors, space of complex vectors. We saw operations on vectors, namely addition, subtraction, and scalar multiplication. Scalar multiplication is called component-wise multiplication of a vector. So these are the only three basic operations I am going to allow myself. With this, I am going to define what is called a vector space. Vector space is a fundamental notion. Let V be a collection or a set of real vectors of size n. V is called a vector space. A vector space is also sometimes called linear space. Sometimes it is called linear vector space if it satisfies the following three conditions. What is the first condition? V is a group under addition. That's a algebraic description. And what is that to be? For it to be a group, if I took two vectors x and y belonging to V, their sum belongs to V. With me? That means it is closed under addition. Closeness is important. For example, humans reproduce humans. Every species reproduces the same species. So under the operation of reproduction, every species is closed. So x is a vector, y is a vector. Under the operation of addition, I get another vector. That's called closeness. In mathematics, closeness is a fundamental property. If you don't have closeness, you are going to go out of the set. If you are going to go out of the set, then you are not in business. So a set being closed under a certain operation is a very fundamental requirement. The next one is called the associative property. If I took addition is a binary operation. For example, if I want to add three numbers, what do? I add the first two numbers, to the sum I add the third number. If I want to multiply three numbers, I multiply 2, and then to the product I multiply the other number. So addition is a binary operation, negation is a unary operation, transpose is a unary operation. To a unary operation you need only one operand, to binary operation you need two operands. X plus y, x transpose, and so on. So if I have 3 vectors, if I want to add, I can add x plus y plus z or x plus y plus z. There are 2 ways of doing it, right? Whichever way you do, the result is the same. That property is called associative property. Associative property is very fundamental. I will give an example very soon. V contains the 0 vector. And what is the property of 0 vector? You add the 0 vector to every vector, I get back the old vector. And to every element x in V, there is a unique y such that x plus y is equal to y plus x is equal to 0. That means I can create the 0 vector from any vector by adding the negative of that vector. So y is called the negative of x. So being closed under addition, being associative, containing the 0 vector, and every element in V has a unique inverse, that's called additive inverse. If they possess all the 4 properties, it's called a group. So every vector space must satisfy these properties. Every vector space must be a group. Secondly, if I multiply any vector, so the first one deals only with addition. The second one is going to deal with scalar multiplication. If I take any vector V, any element of V, x, and any real Ax also belongs to V. That means that the space is closed under scalar multiplication. If you give me 2 scalars A and B, if I want to be able to multiply the vector by AB, what is that you do? You first multiply x with B and then with A. You can also multiply A and B and multiply that. The result is essentially the same. And number 1, if you multiply any vector by 1, it remains the same. If you add 0 to every vector, it remains the same. So what is 0 for addition is 1 for multiplication. And component towards multiplication and addition are the basic 2 operations, and subtraction is related to addition through the inverse. Then the third one is called the distributivity. A times x plus y is equal to ax plus ay. It distributes by multiplication on the left as well as on the right. In general, a plus b equal to b plus a. If a plus b is equal to b plus a, we call it commutative. The order of operation is the material. If a plus b is not equal to b plus a, then it's non-commutative. So everything is commutative. So any set of vectors that satisfies these 3 properties is called a vector space. So what are examples of vector space? There are tons of examples of vector space. The real number R is a vector space of dimension 1. Rn is a vector space of n vectors. Cn is a vector space of complex vectors. The set of all n by n real matrices form a vector space. Even though we use the term vector space as a misnomer, we can simply say linear space. The set of all n by n matrices, I can add 2 matrices, I can multiply a matrix by a constant. It satisfies all the properties. So the set of all matrices is a vector space. The set of all polynomials of degree n is a vector space. The set of all infinite sequences which are square summable. What is this? The sum of the squares of the elements of the series is finite. So that is the summability criterion. So if the set of all square summable sequence, the infinite sequences, that forms a vector space. The set of all continuous functions over the interval AB is a vector space. So even though we call them vector space, the vector doesn't have to be, the elements do not have to be vectors. Everybody is a misnomer. So vector space comes in various shapes and forms. Here are at least 7 different examples of vector spaces. It is these objects we are going to be concerned with in mathematical analysis. Operations on vectors. We already talked about addition, scalar multiplication, subtraction, negation. Everybody? In addition to that, we are going to introduce a lot more operations on vectors. The first of the operation is called the inner product. So in all my discourse, I will use x, y, z belonging to Rn. So what does it mean? Let x, y, z be 3 real vectors of size n. So I simply succinctly state like this: A, B, C are constants, are real numbers. Now I am going to define an operation called the inner product. The inner product is represented by a opening bracket, dot, comma, dot, opening, close bracket. The dot will represent space, dot represents the space. So if I say x comma y within bracket, that represents x transpose y. X is a row vector, x transpose is a x is a column vector, x transpose is a row vector. Therefore, x transpose y is the summation, the product of xi, yi. We know AB is BA for scalars. So xi, yi is also equal to yi, xi. So I could have written it as y transpose x. I could have written it as bracket y comma x. Therefore, inner product of x and y is the same as inner product of y and x. Inner product of two vectors is a scalar. So you give me two vectors, I am going to give you a scalar output. The scalar output is the inner product of the two vectors. Everybody? And it is symmetric. Xy, inner product of xy is the same as the inner product of yx. So what are the properties of inner product? The properties of inner product is this. It should be x cross x. The first y must be x. Please understand that. Inner product of x itself is 0 when x is not equal to 0. Inner product of x itself is 0 only when x is 0. The second y must be an x. There is a correction needed. xy is yx is symmetric. The inner product of x plus y with z, with inner product of x and z and y and z, additive. Everybody? Inner product of a times xy is the a times xy is equal to x times the y. That means if you multiply any one of the vectors by a constant, the whole inner product is get multiplied by the same constant. That's called homogeneity, additivity and homogeneity. If inner product of x and z is the same as inner product of y and z for all z, so x and y are given, z is an arbitrary vector. If I compute the inner product of x with z and y with z, the values of the inner product of xz and yz are the same for all z, then x must be equal to y. Are you with me? So that's a property of inner product. These are the 5 different properties of inner product. In the case of complex vectors, the inner product is defined slightly differently. Inner product of x and y is sum of the product of xi and yi conjugate. You all know what a conjugate is, right? That's right. So in order for the real algebra and the complex algebra to be consistent with each other, the inner product for the complex vector space is to be defined in this way, where bar represents the complex conjugate of a number. So we have seen addition, subtraction, scalar multiplication, inner product. Now I am going to introduce another operation called outer product. What is an outer product? Inner product is x transpose y. Outer product is xy transpose. X is a vector, y is a column vector, y transpose a row vector. So you can see a column multiplied by a row, and what do I get? I get x1 times y1, x1 times y2, x1 times yn, x2 times y1, x2 times y2, x2 times yn, xn times yn, x1 times y2, xn times yn. Are you with me, please? I am going to create a matrix out of two vectors. This is called outer product matrix. So you can look at the structure of this. The first column, look at that, all the x, this is the vector x multiplied by y1. The second column is the same column x multiplied by y2. The nth column, the vector x is multiplied by yn. So I can think of this, each column of the matrix is a constant multiple of the same vector. The multiplying constant is y1, y2, y3, yn. Or you can look at the row. I have the row y, y1, y2, yn. Every element of the row is multiplied by x1. Every element of the row is multiplied by x2. So the multiples of the row y. Everybody with me, please? So either it's the multiples of column x or multiples of row y. Are you all with me now? That's right. That means every column is generated from the same column. Every row is generated from the same row. I'm sure everybody knows the notion of what's called linear independent, right? So every column is a multiple of the same column means what? All the columns are linearly independent. All the rows are linearly independent. I'm sorry, linearly dependent. All the columns are linearly dependent. All the columns are rows are linearly dependent. There is only one column that is linearly independent. There is only one row that is linearly independent. You also know the notion of a rank. The number of linearly independent rows are columns. So you can really see outer product matrices, by definition, they are rank 1 matrices. Now I am going to introduce another measure. Vectors are object. If I have real numbers, how do I measure the size of a real number? Absolute value. Absolute value of a real number tells you the size of that number. Absolute value of -3 is 3. Absolute value of 10 is 10. Absolute value tells you the distance of that number from the origin. It measures the length of the distance from origin to that place. So absolute value is a measure of the size of a number. Absolute value of a real number, absolute value of a complex number. We all know how to compute absolute value of a complex number. A plus IB is absolute value square root of A square plus B square. Everybody, you remember that. Now, if I have a vector, how do I measure the size of a vector? And that quantity is called the norm of a vector. The norm of a vector refers to the size of a vector. The norm of a vector is denoted by the two vertical symbols with the x in between. The norm of a vector is a scalar. The scalar denotes the measure of the size of x. Everybody with me, please. There are various types of norms. For example, human weight, I can measure it in kilograms, I can measure it in pounds. Length, I can measure it in centimeters, meters, kilometers, miles, furlongs. There are several measures for weight. For volume, liters, gallons, ounces. With me? Likewise, for measuring the size of vectors, there are different ways of measuring. One is called the Euclidean or 2 norm, is denoted by the subscript 2. And what is that? That comes from the Pythagorean theorem. It's the square root of the sum of the squares. We all should know that. And what is that? That is essentially the square root of the inner product of vectors itself. That's called 2 norm, Euclidean norm. The geometry that you learn, that you start learning in your 7th grade or 8th grade, you are introduced to Euclidean geometry. 2-dimensional Euclidean geometry, triangle, hypotenuse, Pythagorean theorem, length of the hypotenuse of a right angle triangle with side A and B is square root of A square plus B square. And that's exactly the first norm. The second norm is called the Manhattan norm or a 1 norm. For example, if I am going to go from point A to point B, I can fly. The crow's flight is essentially what Euclidean norm is all about. But if I want to go from IIT to Mylapore, I have to follow the road. I can't fly. Yes, I could fly, but there is no facility, right? So what is that you do? You go 2 miles east, 1 mile north. Everybody? The length of the sum of the length of the segment of the roads that you travel. So I have origin, I have a point x. To go from 0 to origin, I have to travel the sum of the distances of each component. Are you with me? In a 2D, if I want to go from 0 to x1, x2, I have to go x1 plus x2, the length of x1 plus length of x2. So that's what's called the sum of the absolute value of xi. This must be xi. Are you with me? That's right. Then there is an infinite norm or a Chebyshev norm that's denoted by subscript infinity. What is that? That's a maximum of the components, maximum of the absolute value of the components of the vector x. In mathematics, Chebyshev norm is very useful. Then there is what's called a Minkowski norm or a P norm, subscript P. that is essentially the sum of the pth power of the absolute value of the components. You take the pth root. The pth root of the sum of the pth power of the absolute value of the components. With me? Then there is what's called an energy norm. I have not introduced matrices, but I simply want to anticipate. You all know that. A is a matrix, X is a vector, X transpose is a row. So row times a matrix times a column is a scalar. That's called a quadratic function. So square root of the quadratic function. A is a symmetric positive definite matrix, and that's called the energy norm. If A is an identity matrix, that becomes a 2 norm. So the 2 norm can be generalized to energy norm. So now you see, what is P? P norm. P can be anywhere greater than 0 up to infinity. So P norm, 2 norm, 1 norm, infinity norm, energy norm. And what are these like? These are like pounds, kilograms, with me, centimeters, meters, liters, ounces, gallons. So we have various units, here also various units. I can measure the same distance in kilometers or in miles. I can measure the same mass in terms of pounds and liters. Pounds and kilograms. I can measure the same volume by liters and ounces and gallons. Everybody? Likewise, I can measure the norm of the same vector in different ways. In different calculations, different norms tend to be useful. If I have a norm definition, then I have a concept of a distance between vectors. So x and y are 2 vectors. So you can think of it 2 points in n-dimensional space. What is the distance between the two? X is a vector, y is a vector. I can subtract the 2 vectors x and y. The difference of 2 vectors is a vector. The norm of the difference of the 2 vectors is the distance between the two. So if I pick the norm to be 2 norm, I get a 2 distance. If I pick the norm to be 1 norm, I get 1 distance. If I pick the norm to be infinity norm, I get the infinity distance. With me? So the distance between 2 norms can be defined in several different ways, much like we can express any quantity in various different units. With me? In all of mathematics, different people use different norms because for some certain problems, certain norms are more easy to work with than others. That's the idea. So now we talked about various norms. So I want to now ask myself, can I generate my own norm? Should you deal with only the norm that others have done? The answer is yes. So now I am going to talk about what is that to be for something to be called a norm. So if you want to create your norm, what is an algorithm for which, using which you can create your own norm? Are you with me? That's what I'm going to talk about. So let's call n as a norm of a vector. So norm associate a number with each vector. So what does it mean? Norm maps vectors to real numbers. The norm can never be negative. Size, distance, weight can never be negative. So nx is called the norm of x. For it to be a norm, it satisfies 3 conditions. One is nx is greater than 0 when x is not 0. That means if a vector is a non-zero vector means what? At least one component is not 0. So if the vector is not 0, it must have a non-zero measure of its size. The norm is 0 only when x is 0. If you multiply a vector by a, the norm gets multiplied by the absolute value of that. With me? That's called elongation of a vector. Elongation of a vector. Shrinking the vector. If I multiply a vector by a quantity less than 1, it shrinks. Greater than 1, it elongates. The third property is called triangle inequality. What is that? We all know. What is the basic property of triangle inequality? the third side is always less than the sum of the other two sides. All of you with me, please? So that's how we learn geometry. So we learn geometry through two norm. Now we are trying to generalize the properties of two norm to any vector, real complex. With me? That's right. And now we talked about vector spaces can be of any type. So I should be able to talk about the norm of a function, norm of a sequence, norm of a matrix, norm of a vector. Are you all with me? All the mathematical objects I should be able to consider the norm. I'm simply talking about in the context of vector space, and vector space comes in various shapes and forms. So this cuts across all of the domain that we will be interested in data science. Sometimes we may be interested in matrices, sometimes in sequences, sometimes in vectors and matrices, and so on. Of all these norms, only the two norm is derivable from inner product. Let's go back to the definition of an inner product. X inner product X, what is that? Is the sum of the square of xi. Square root of the sum of square of xi. That's called the two norm. Two norm is the only norm that is associated with the inner product. So if I can define an inner product, I have a two norm automatically. Two norm is derived from inner product. Now I am going to give you a small homework. Verify that the square of the norm of x plus y and x minus y is equal to 2 times the squares of the norm of x and y. Now please understand, the two norm is equal to inner product. So if you express this using inner product, you can verify this. This is called parallelogram law. I would like each of you to be able to work with this these kinds of simple homework as we go by. Now I am going to tell you using pictures how to differentiate the behavior of the norms. We all know the notion of a unit sphere. What is unit sphere? Unit sphere is the locus of all points which is at distance 1 from the center, which is the origin. Until now we did not know any other way of measuring distances other than Pythagorean theorem, Euclidean distance. Therefore, if you consider a unit sphere as the locus of point whose distance is 1 from the origin, where the distance is measured using two norm, it looks like this. That's why we call it sphere. That's why it's called unit sphere. Why? The distance to any point from the center is 1. But if I change the norm, with me? If I change the norm, the shape of the unit sphere changes. In one norm, what did I want? The absolute value of x1 plus absolute value of x2 must be equal to 1. So any point in the two-dimensional plane has coordinate x1, x2. Everybody? I want the absolute value to be, sum of the absolute value to be equal to 1. So in here x1 is positive, in here x1 is negative, x2 is positive, x2 is negative. Everybody? So a little reflection, I want you to check this, don't take it from me. You should always believe your teacher, but never to believe him 100%. You should always suspect, you should always check. Are you with me? So what is the homework for you? Prove to yourself that the two norm unit sphere is this, which you already know, that's why you call it sphere. A ball is a sphere. The unit sphere in one norm has this rhomboidal shape. The unit sphere in infinity norm has this shape. The unit sphere in energy norm, when I pick the matrix A to be 5001, to be this. Everybody with me, please? The geometric ideas are same. So what does this mean? The shapes depends on the concept of a norm. Until recently, there was no need for us to be able to do anything other than the two norm. Now we are opening newer doors to be able to interpret geometric quantities with me. So I can do geometry using many different types of norms. With me? So what is the difference between geometry and analytical geometry? In geometry, you talk about 1D geometry, 2D geometry, 3D geometry. When you go beyond 3D, you can't explain anything using pictures. You have to convert it into algebraic expressions. So analytical geometry is the geometry of high dimensional space. Geometry is the geometry in the low dimensional space. Linear algebra and vector space theory helps you to develop these tools in analytical geometry to be able to analyze objects in a multi-dimensional space. Why are we interested in that? Data science deals with objects in multi-dimensional space. So understanding the properties of multi-dimensional space is a part and parcel of data science. All of it with me? Come on, guys. That's right. So what is a unit vector? Unit vector is a vector divided by the length. So the standard unit vector is the unit vector in 2 norm. I can have a unit vector in 1 norm, unit vector in 2 norm, unit vector in p norm, unit vector in infinity norm, unit vector in energy norm. So if you go to this, what is this? Each picture tells you the locus of a unit vector. Are you with me? That's right. And now that's an important component is called Cauchy-Schwarz inequality. With me? So what is that? X is a vector, y is a vector. The inner product of x and y is x transpose y. Inner product of x transpose y is equal to the product of the norm of x, norm of y times cosine of the angle between the two vectors. So x is a vector, y is a vector, there is an angle between the two. The inner product of two vectors is essentially xi, yi summation. Another way of looking at it is the norm of the vector x, norm of the vector y, cosine of the angle between the two. So there are two ways of looking at the inner product. Since cosine is always less than or equal to 1, the absolute value of cosine is always less than or equal to 1. Everybody with me, please? So this product is always less than the product of the 2 norm of x and the 2 norm of y. Everybody? The two are equal only when cosine is 1. When cosine is 1, theta is 0. So the inner product of two vectors is the product of norms only when the vectors are collinear. If they are not collinear, there is an angle theta which is not 0. So if you are going to multiply norm of x, norm of y by cosine of theta is less than 1, the inner product is always less than or equal to the product of the norms. All of it me? Everybody with me, please? And that's what is being said in here. Inner product of x and y is equal to x transpose y. With me? This is called Minkowski's inequality. This is called Cauchy-Schwarz inequality. So what is Cauchy-Schwarz inequality? Inner product of x and y is always less than or equal to the product of the norms of x and y. Minkowski's inequality is essentially saying that I am considering the product of the p norm and the q norm. And how do I pick p and q? 1 over p plus 1 over q is equal to 1. If p is half, q is half, automatically that. If I'm with me, that's the idea here. Now we have various norms. I can convert miles into kilometers and kilometers into miles. In India we use kilometers, in America we still use miles. In India we use kilograms, in America we still use pounds. In India we use liters, in America they use gallon. So I have a translation table. 4 liters is roughly 1 gallon. 8 kilometers is 5 miles. With me? That's right. 2.2 pounds is 1 kilogram. So we are going to relate every way of measuring. So if you tell me in one thing, I can convert it into anything else. So if you consider norms, how do you convert one norm to the other norm? What is the relation between the norms? Are you all with me, please? So one norm is bounded by a lower bound and upper bound. So one norm is bounded, sandwiched by multiples of 2 norm. 2 norm is multiplied by, is sandwiched by multiples of infinite norms, and one norm is also sandwiched by multiples of infinite norm. So what does it mean? All the norms are essentially equivalent. So that frees you up. You don't have to do a particular problem using only one norm. So you do your problem any way you want. If you get one good result, I can then translate that result using this conversion table to any other norm that you want. Are you with me, please? Everybody. So we need to be able to have that freedom of analysis. The freedom of analysis comes from the fact that there is a fundamental intrinsic relation between the norms to the level that all the norms are equivalent. That means when the analysis, one can pick any norm that one likes. Now we are going to go to the next concept called functionals. Function, functional. That's a characteristic difference. I'm sure you all know how to define a function, right? There is a domain, there is a range, and there is an association with that. Functionals are special forms of functions. So functionals are function defined over a vector space which takes values in the real domain. So any function that maps V into R is called a functional. A function has an input and output, right? It takes a vector and puts out a number. For example, a norm is a functional. A norm represents a number that represents the size of the vector. So functionals are special forms of functions. With me? Inner product maps vectors to scalars. Outer product maps vectors to matrices. Norms maps vectors to numbers. So one specific form of function is called a functional. A functional is said to be a linear functional if x1 and x2 are the input, the output is f of x1 plus f of x2. Everybody is in my place. If I multiply the input by a constant a, the output also gets multiplied by the constant a. So any functional that satisfies the additivity and the homogeneity property is called a linear functional. Now I am going to give you some examples. Norm is a nonlinear functional. I want you to verify this homework problem. Please do all these homework problems. So norm is a functional, norm is a nonlinear functional. So what is that you have to show? Norm does not satisfy one of these. Norm of a sum is less than or equal to the sum of the norms. Triangle inequality. So that's a proof of that. That's right. If A is a fixed vector, I can define an inner product f of A of x. Now the inner product of every vector x with A, I am going to define as f of subscript A with x, and that's a linear functional. Given a matrix A, f subscript A of x is 1/2 of x transpose Ax. That's a nonlinear functional. With me? Come on, guys. That's a nonlinear function. So function, functionals. Examples of functionals. The next one is called the orthogonality and conjugacy property. y1 and y2 are two orthogonal vectors written as, x and y are two orthogonal vectors denoted by x perpendicular to y if the inner product is 0. Please understand, inner product of two vectors is equal to the product of the length of the two vectors times cosine of the angle between the two. If the cosine of the angle is 90 degrees, cosine of 90 is 0. With me? So inner product is 0 when the two vectors are perpendicular to each other. X and y are said to be A conjugate if x transpose AY is 0. If A is identity, that becomes inner product. So conjugacy is an extension of the concept of inner product. With me? So now I am going to give you two definitions now. Let S be a set of k vectors. Xi belongs to Rn. That means I am having a collection of k vectors, each of them are vectors in n dimension. With me? If you have a question, please feel free to ask. We say the set of vectors is said to be mutually orthogonal if the inner product of xi with xj is 0 for I not equal to j. It's not 0 when I is equal to j. That means every pair of distinct vectors are orthogonal. With me? Inner product of x with itself can never be 0. It's the square of the length of the vector, right? With me? So I is equal to j, the inner product is not 0. I is not equal to j, inner product is 0. If the vector x has a unit length, if the vector y has a unit length, and if their inner product is 0, they are called orthonormal. The inner product is 1. So orthogonal system, orthonormal system. With me? That's right. A system of vectors is said to be A conjugate if xi transpose AXJ is 0 for I not equal to j, is equal to the energy norm of x with respect to the matrix when I is equal to j. That's called A conjugate. So A conjugacy is an extension of the notion of orthogonality. So orthogonal, conjugate, mutually orthogonal, mutually orthonormal, mutually conjugate. These are the various concepts that comes out of this. They are all extensions of the concept of orthogonality. Everybody?
Sir, that A matrix you mentioned, right, in A conjugate, is there any condition on that matrix that it should be diagonal?
It must be symmetric. No, not necessarily. It must be symmetric and positive definite. If A is diagonal, identity is a diagonal matrix, all one, right? So conjugacy is an extension of the notion of orthogonality. Now I am going to come to the notion of what's called linear combination. With me? So x is a set of vectors. Each vector is an Rn. There are k such vectors. So S is a collection of k vectors, each in Rn, where every vector has n components. Everybody with me, please. Let a1, a2, ak are real numbers. Then a vector y, which is the sum of the scalar multiples of the vectors in x, is called the linear combination. So y is equal to a1 x1 plus a2 x2 plus ak xk. And what is an example of a linear combination? If I pick ak equal to 1 over k, is equal to summation xi over 1 over k. What is that? That's called the centroid, average. With me? So the average of a set of vectors, the centroid of a set of vectors, is a linear combination. That's an example of that. Now I am going to go to the concept of linear independence. A set of vectors in S is said to be linearly. To define independence, I am first going to take dependence, and independence is non-dependence. Okay? So a set of vectors S is said to be dependent if there exists a linear combination that can annihilate it. That means given x1, x2, xk, I can find constant a1, a2, ak such that if I multiply a1, x1, a2, x2, ak, xk, I can create the zero vector. If I have the ability to do this, we say the collection of vectors x1, x2, xk are linearly dependent. A set of vectors is said to be linearly independent if it is not linearly dependent. So what does it mean? There exists no set of constant a1, a2, ak such that a1, x1, a2, x2, a3, xk can never be 0 for any value of a1, a2, ak. Will me please? That's a concept of a linear dependence, linear independence, linear combination, linear independence, linear dependence. I'm sure you all have heard of all these things. I just want to be able to brush it up and so on. Now I'm going to introduce the notion of what's called a span of a vector. Let x1, x2, xk be again a subset of vectors in Rn, finite subset. With me? The span of vector is simply the set of all linear combinations. The span of the vector consists of the vector y, where y is expressible as I is equal to 1 to k xi ai xi, where ai's are real, xi's are in Rn. So x1, x2, xk is given to you. You have the choice for a1, a2, a3. Each ai is a real number. There are infinitely many choices for a1, infinitely many choices for a2, ak. So if I consider all possible combinations of this, I get a space which is getting bigger and bigger and bigger and bigger and bigger. That space so created is called span of x. All of it me? Span of x. Clearly, span of x is a subset, is a vector space. It is a subset of Rn. Are you with me? So let's consider R3. The two-dimensional plane x1, x2 is a subspace of R2, but it's a vector space itself. Everybody? Then in other words, a subspace can inherit the same property as the whole. So span is also called subspace generated by S. For example, how do you generate 2D? I have two unit vectors, 1, 0, 0, 1. Every vector in the two-dimensional plane can be generated by x1 times e1 plus x2 times e2. x1 and x2 are real. So the entire two-dimensional plane is generated by two vectors, e1, e2. They are called basis vectors. So that brings us to the notion of basis and dimension. If B is a finite subset of a vector space, that means I have a vector space. Vector spaces are infinite in nature. There is, are you with me? Vector spaces are infinite in nature. B is a finite subset of vectors from that infinite. If every vector x in V can be obtained as a linear combination of the vectors in B, then B is said to generate V. You remember? Span generated by S. Every vector of the span is generated by linear combination of the members of the set S. Then we call B the generator of V. For example, E1, E2, 1, 0, 0, 1 is the generator for R2. R2 is a vector space. If the set of vectors in B are linearly independent, see, I first said only a finite subset. Now I want them to be linearly independent, then B is called the basis. With me? The basis for the span of S, and S is equal to V because B generates V. The ith unit vector with 1 at the ith element, 0 elsewhere is a standard basis for Euclidean geometry. So Bn is a set of all Ei, I running, this is little I running from 1 to n is the basis for Rn. The number of elements in B is called the dimension of the space. So what is the dimension of the space? R2 is, we call it 2. Why? Using two vectors I can generate everybody. Everybody, all of it with me please? So any finite subset that containing linearly independent set of elements whose linear combination can generate the whole set, that subset is called generator. The number of elements of that set is called dimension. Now these are not the things that I generated. It's a common knowledge. It's a very well established theory. The books I refer to are these three books. I have copies of all these three books. I'm sure your library has all these three copies. How do I know? I was a faculty in the Department of Computer Science from 1973 to 75. My first job was, I was a member of the inaugural faculty of the Department of Computer Science way back, but I was here. I know your library very well. I know your system very well. I worked in this place. So with that, I conclude my first of the concrete part of the course, which is theory of linear vector spaces. With me? We will continue in this vein starting tomorrow. Just to remind you, we will start at 9:15. We will have 1.5 hours of first session. 9:15, 1.5, that puts you to 10:45. 10:45 to 11, Sridhar has promised that we'll have coffee. I'll remind him. And then from 11 to 12:30, we'll have second session. Thank you all. I will see you tomorrow. Bye now. And enjoy working these problems. And if you have difficulty after recording or in between, I can help you. With me? Thank you all. Bye-bye.